In this video, I want to talk about a very important theorem that's at the end of section 3.2 and do an example that ties together the three most important concepts we've talked about so far in the course: limits, continuity, and the derivative. But to start off, a theorem. If f of x is differentiable at x equals c, then f of x must be continuous at x equals c. You'll hear people say that differentiability implies continuity. That, if you're differentiable at a point, then you're automatically continuous at it. This goes nicely with the ideas at the end of the last video, that if I have a discontinuity, I can't possibly be differentiable. This theorem is saying that, hey, if you're differentiable, you're automatically continuous. That, if the slope of my tangent line is going to equal a number, then at that point in the graph, there can't be a hop, skip, break, or jump. Differentiability implies continuity. So, the example I wanted to do. I have a function called f of x graphed here, and it's a weird piecewise function. And I have three questions, two of which we've seen in a different example and on lab number 2. Here we're asked to find any values c where the limit as x approaches c of f of x fails to exist. In 2, we're asked to find any values of c where f of x fails to be continuous. And then finally, the new part for us here, we're asked for any value c where f prime of c does not exist. All right, so 1 and 2 questions we've considered before. Number 3, new to this grouping of things, but I feel like these three questions always go together. All right, find any value c where the limit does not exist. Well, at c equals 1, I have different one-sided limits. The limit, in fact, as x approaches 1 from the left-hand side would be 1, and the limit as x approaches 1 from the right of f of x would be 2. All right, so that limit doesn't exist because my one-sided limits don't agree. Looking from left to right, all of these places are good, even that one with the hole, because the limit from the left and from the right both look like they're 1, but the limit doesn't exist at 5. Because while I would write the limit as x approaches 5 is infinity, those limits don't really exist because that's not a number. All right, so I have 2 spots in that graph where my limit fails to exist, 1 and 5. All right. Find any values c where my function's not continuous. Well, what I'm really thinking about here is the continuity test, which would tell me that to be continuous, f of c must exist. 2, the limit as x approaches c must exist. And 3, those two numbers are the same. Okay, well here's the big point. If the limit must exist to have continuity, any answer I just put here is also an answer for number 2. So c equals 1 and 5 are out because the limit fails to exist. And I'm just going to say c number 1. Because in number 1, I say the limit doesn't exist for those. They break the second part of the continuity test. All right, so I got 1 and 5. Let's see where else I might not be continuous. And I'm really concerned about this spot right here. At c equals 4, f of 4 does not exist. So I see 3 discontinuities: a jump discontinuity, an infinite discontinuity, and here I have my removable discontinuity. All right. 2 places where the limit doesn't exist that automatically become answers to the question about continuity, and then 1 more place where I have a discontinuity. Find any value c where f prime of c does not exist. Anywhere I'm differentiable, I'm continuous. And if I think back to that list of places where derivatives don't exist, one of the things we listed were discontinuities. So any answer to number 2 is automatically an answer to number 3. So at c equals 1, 4, and 5, my derivative does not exist because I have discontinuities. I could just say C number 2. All of those places, 1, 4, and 5. Now I think about the other places where I might not have a derivative. And the places I'm thinking about now are corners, cusps, and vertical tangent lines. Those were the other examples that weren't discontinuities. And so corners and cusps, I'm looking for sharp places in the graph. Oh, and there's a corner, right? That looks like an upside down absolute value graph. And here's a more subtle corner, right? Here the slope on the left-hand side would be positive 1. On the right-hand side, it looks like I go down 2 and over 2, that'd be minus 2. The left-hand slope and right-hand slope don't agree. And here, on this side, the slope would be 0, and on this side, it would be that minus 2. So I need to add to my list 2 and 3. Those are corners. 2 places where the limit doesn't exist. 3 places where the function is not continuous. 5 places where the function does not have a derivative. All right. Talk to you later.